All right. So what are we going to do today? I thought we needed to just kind of, since it's been a couple weeks, add in the delta G piece to the equilibrium piece to what we were doing on that lab with the electrochemical cells, and then start looking at the reverse process of electrolysis and see how far we get with that today. So if you want to open up, it was a few segments back. I don't know if you still have it handy, but where is it? The one that said Voltaic Cells Lab. And it looks like something, this. And then within that, there was a link that opened up kind of the experimental part. Ooh, okay. You zoom in. And I just want to work through a couple of these with you. So actually, let me download this so I can write on it. And then we're just going to go through the basics, and then I'll add on the new thing. And hopefully that'll be good. And that'll mostly take care of the voltaic cells, except where you may have questions and uncertainties. But had we gone through any of these together? I don't remember. Did we finish any of them? No? Okay, so let's just start with the first one. And, whoa, gotta get my zoom right. I gotta zoom on my zoom. All right, so first of all, in order to solve this problem, we need the reduction potentials. So let's think about what's going on here. On the one side, you obviously have zinc and zinc ion, and on the other side, you have nickel with nickel ion. So when you go into that little lab simulation, it's going to let us pick not only what the electrodes are, but also the solutions and their concentrations. So this is first we're going to do the standard cell. I think last time we did talk about Nernst, but I'll look at that again with my second example just to review it. But let's, before we actually put the lab in, let's predict. So if we go to our standard reduction potentials here, and let me zoom in so we can actually read this, we were looking for one that had zinc and zinc ion, and I think that's around here somewhere. I think so, haha. So let me grab this one, just so I have it in front of us. Okay, there's that. And then I'll fix the font in a second. The other one I believe was, what was the other one? Nickel. And again, we have to make sure we're picking the right one. So we want the nickel 2 ion going to neutral nickel. So that looks like this one. And remember, these are always given as reduction potentials. And then we have to figure out which thing is doing what. Well, how come that one worked? That one gave me an arrow. This one, oh, that's weird. Okay, whatever. Okay, so as we have said, since these are reduction potentials, oh, I see it didn't. Okay. We have to remember that the one that has the more positive, higher positive value is the one that's more likely to be reduced, right? So that's the first key point. After that, it's easier to read, I'm sorry. Half my life is fixing fonts. Anywho. So just based on that, let's see if we can figure out what is the half reaction in each case, what's oxidized, what's reduced. And to do that, we're also going to predict the voltage of the cell. So let's go through that whole process, just to review it. So first of all, if we look at these numbers, can you tell me which one should be oxidized and which one should be reduced? And be specific. What actual thing in this system is going to be oxidized, meaning going to go from lower oxidation state to a higher, more positive number? Which one's oxidized? What do you think?
I think the zinc ion is being oxidized to.
You're, you're close. It's not the ion though, and that's what you got to be careful of. It's the
Mhm.
zinc as the metal. Because remember,
Oh, okay.
it's going to go the other way, this reaction. So
Okay.
definitely, yeah, the zinc, and that's what I meant when I said be specific, right? Like because the metal versus the ion, and then the thing that's reduced is what?
Is that nickel metal then?
The nickel metal
Yeah.
or the ion this time?
Um.
So if that's confusing, look at it
Yeah.
this way. Let's get the reactions going in the right order, meaning that we know the second reaction has the higher, more positive potential. So it's going to go the way it's written. So the half reaction, in the actual way it's going to happen, is this way. So in this case, you can see it is the ion being reduced to the metal. And since the other one has to flip around, the metal is the actual reactant this time, right?
That makes sense.
Yeah. And this system's already balanced by the fact that we have 2 electrons in and 2 electrons out, so we don't have to do any multipliers or anything. And the overall reaction would then be the zinc metal reacts with nickel ions to produce zinc ions plus nickel metal. In other words, all that's really happening is electrons are being pulled off of zinc onto the nickel ions, and they're doing that through the cell. So this is each half reaction and the overall reaction. Just to make sure we're clear then, the first one that I wrote is the reduction, and the second one is the oxidation, half reaction. Okay. Now, to find the overall, and I think that's coming further down here where it says find the theoretical voltage. To find the theoretical voltage now of the entire process, we have to take what happens at the cathode. And again, we're doing this in the way that keeps us, we don't have to like flip signs, we're just going to keep the reduction potentials and do the cathode one minus the anode one. Or another way to think of that is the one that's actually reduced minus the one that's oxidized, right? Because that's really what's going on, anox, red cat. In our case, quite simply, the cathode is where the reduction happens. So that's the nickel reaction, right? And that's negative 0.23. And then we're subtracting what's happening at the anode, which is the oxidation. Now you might say, well, wait, if it's oxidation and we flip the equation, shouldn't we flip the sign? Well, we kind of are and we kind of aren't, because instead of flipping the sign, we're just subtracting the negative, right? If we had done that the way we're saying, like the way it's showing here, I would have had a flip this one, it would have been positive, and then I would have been adding it to this negative, and I'd get to the same basic place. But it just seems simpler to just take the difference of the numbers that we already have. So when we do this, the predicted voltage, negative 0.23 minus negative 0.76, I get a positive 0.53 volts. And that, of course, is assuming that we're using the standard cell conditions, like 1 molar everything and all that sort of stuff. So now, let's go to that little experimental window and see if we get about 0.53 volts on the experiment. This one. Okay, so let's see. The black one is the negative. The negative on these is the anode. Which one should I connect here? Is this the nickel side or is this the zinc side? Which one's the anode again?
Is that the zinc side?
The zinc side, because that's the one that should be oxidized, right? And let's see, the solution would be like zinc nitrate. So our nickel should be the cathode side, which is the positive terminal in its solution, which was nickel nitrate. And now if we connect the magical device and everything's at 1 molar, No, 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 0.513. Close enough. Okay, we got about 0.53. But anyway, so experimentally, we're not always going to get the exact same value, which is fine. Okay, we don't have to worry about all the percent error stuff. That we would have done if we were actually doing this in the lab. So let's try to figure out which way do the electrons flow on the diagram. Where's my dot go? So if I go back here, are electrons flowing from the zinc to the nickel or from the nickel to the zinc? Which way do you think they're flowing based on this reaction system?
From the zinc to the nickel.
I agree. That's the whole thing, right? Because, and I'll just write as 2 electrons per cycle, because the zinc is losing those electrons and they're being pulled over to the other side through the nickel to effectively neutralize the nickel metal onto the nickel electrode. So that's the flow of electrons. Um, the next question asks us to write this in line notation. So for line notation, we just have to kind of write it the way it flows, meaning like we know that we start with zinc on the anode side in a solution of zinc ions, salt bridge, so that's the oxidation first, then the reduction is showing the nickel ions, and then the nickel solid. So that's all it really needs for the line notation here. Again, just a simple representation. Now it asks the electrode that is gaining mass. How is an electrode gaining mass? Well, think of it this way. On one side of the system, ions are being turned back into metal and they're sticking to the electrode first, for example. So like here, where the reduction is happening, we should imagine that more and more nickel is being plated or deposited on the nickel in the solution, right? Because that's where the reduction is happening. The zinc here is dissolving. So if we were to weigh these after some time, we'd pull out the zinc electrode where the oxidation was happening, and it would weigh less than we started because some of it's dissolved. The nickel, however, if we pulled it out, would weigh more because nickel has been sticking to it as it formed back into neutral nickel metal. So in general, we should expect that the cathode here, where the reduction is happening, that's where we're going to get the increase in mass. So in this case, the nickel electrode is the one that's gaining mass, or you could call that, of course, the cathode, which is what it is. Everybody still cool? All right. The flow of ions on the salt bridge. Remember, for this to make a complete electrical circuit, since negative charge is leaving from this side, negative charge has to replace it. So in terms of whatever the ions happen to be, I think in the lab we would have used like a potassium nitrate solution for the salt bridge. It's pretty typical. Since again we're losing negative out of this side, for the purpose of charge balance, the negative ions have to come in here to replace them. Otherwise you're going to get an imbalance of charge within the beaker. And if that happens, you're going to get a back voltage which stops the whole thing. That's why you need the salt bridge in the first place. And then of course the positive ions are going to come this way to compensate for the negative charge that would be accumulating of the electrons coming in and taking out the positive ions and turning them neutral. So that shows us the basic flow. Overall, what it represents is negative charge flowing around and around in this direction. Whoops, I lost my dot again. Any questions on that? Okay. So the last thing, the thing that we were not able to do until really today or yesterday, depending on when you had class with me, is the Gibbs free energy. So I'm going to teach you something new here, and it's connected directly to something you may have learned in physics if you took physics. And if you didn't, that's okay, because you don't have to know. I'm just going to tell you the results. So it turns out that we can connect, just like we did with equilibrium and thermodynamics today, we can connect thermodynamics to the cell potential. So delta G is our friend, the in this case standard free energy change. N is the number of moles of electrons, kind of like we saw last time when we did Nernst. F is that Faraday's constant we learned last time, and I'll remind you its value, but it would be given on the resources for the exam. It was 96,485, and that's the number of coulombs, which is a unit of charge, per mole of electrons. So if you think about what's going on here, this product is the total charge that's flowing, because you're saying how much charge is it per mole times how many moles of electrons are carrying it. And then of course, this is what we just calculated earlier. It's our cell potential overall. Now, I know a couple of you took physics, 2/3 of you. So I'm just going to show you this for the sake of argument and see if you remember any of this from physics. I don't know how much electricity you guys do anymore, but did you ever do something about like the work of moving a charge through an electric field? And that work was equal to negative QE? Does that look familiar to you from physics? Hey, Mr. Chen. Yeah, I'm in class. That's okay. I'll come find you in a little while if you're around. Okay, so if you remember that, the only reason I'm bringing it up is because it really just fits right into what we're saying here. Because delta G, we have said chemically, is kind of the work you can extract from the system. But what we're putting in terms of charge through the system is this total kind of moles of charge, and this is the potential difference it's moving through. So really this is directly from physics if you think about it. I just thought that's a nice connection if you've seen it before, but you don't need it to do what we're going to do. The problems are actually really easy once you know that this is the relationship. And again, just to show you what it looks like, this is how it looks on the AP reference sheet, how they stack it all up. So you'll notice under the thermodynamics equations, they give you all those summation things, but they give you delta G in 3 flavors. The first way we learned it, how we connected it to the equilibrium constant today or yesterday, and now how we're connecting it to the cell potential. So they're just showing you another version of that same equation. Now, here, because we've calculated the cell potential, we can easily calculate the delta G as long as we're careful with our units again. So once again, we have another experimental way to determine free energies. You build a chemical cell, and if you can measure the voltage, you can find the free energy of it. This directly connects to the concept of batteries again, because these are the kinds of chemistry you do in a battery, and the battery has so much work it can do, in a device, and that's kind of calculable sort of through this. So first let's go back to our balanced equation, because when I ask for the moles of electrons transferred, what I'm really looking at is kind of how I balance this redox equation. So you'll notice it's the 2 electrons that are moving, right, from one to the other, total. And therefore, that's what our N is here. It's 2. Whoops. This thing's moving really fast. Okay. So negative, and then I have the 2 moles of electrons, and I'll put the units in very explicitly here for clarity. And now I multiply that by 96,485 coulombs per mole. And then I just have to multiply that by the voltage. Now for clarity, we need to define some units here from physics. Again, if you took physics, you might remember this. If you didn't, I'm telling you ahead of time. You learned something from physics? Now, what we call volts, the unit, let me write this, volts, is really the energy per unit charge. So it's the joules per coulomb. So coulomb is a unit of charge. J is our friend, the joule. And so when I plug this in, when I get the voltage that I found here, I'm going to write it as joules per coulomb so that you can see how the units actually come out to something logical. And that's just the 0.53 volts here. So 0.53 joules per coulomb. Now you can see these are going to be big numbers, and ultimately we end up dividing them by 1,000 to put them in kilojoules. It doesn't really matter, but just so you know what I'm going to do. Now I'm going to do -2 times 96,485 times 0.53. And I get somewhere in the neighborhood of negative 102,274 in joules, because if you look at what's left, that all canceled out. And if we divide that by 1,000, we get about negative 102.3 kilojoules for the free energy, the standard free energy here. Now notice, from what we learned today or yesterday, depending again which day you took this class lesson, couldn't we also, now that we know delta G, use this to find the equilibrium constant? Because we have a connection there as well. So it's like a three-ring circus of three of the big areas of chemistry: electrochemistry, thermodynamics, and equilibrium, all beautifully connected to each other, all looking at similar idea from different angles. Any questions on this so far, how I employed this new equation?
Wait, I have a question. You said you could connect it to the equilibrium constant, right?
Mhm.
But what is the temperature here then?
Good question. Anytime you see that little degree sign, we're always assuming standard temperature.
Oh, okay, so 298.
Right, exactly. Good question, because that makes a difference. In fact, these cell potentials are different at different temperatures, as we saw with the Nernst equation. And again, I'll bring that back in my next example, just so we can see that again. Are we good, though, on how this whole page kind of flowed then? This kind of question? Okay. So with that example, you could do the similar thing for like these next couple if you needed, just for your own practice, because they're essentially the same with just different cells. Um, so let's go into one of these Nernst ones, because I think it also asks us to find the equilibrium constant at least once, and I think it's worth looking at that. Yeah, this one does. Perfect. Okay, so the difference here, of course, is that our concentrations are different, right? They're no longer standard. But we're still going to have to calculate the standard value and then tweak it, because as we said, and just again to show you that it's there, in that same section on thermodynamics and electrochemistry, the very last equation is the Nernst equation that we looked at last time. So let me just kind of rewrite that, because I know I'm going to have to use it here and I just don't want to forget it. So Nernst, we get the non-standard cell potential by tweaking the standard cell potential. Now, that might look more familiar now since what we learned just the other day. If you recall a moment, well, maybe depending again which day you were in class, uh, we looked at an equation that looked very similar for delta G. Remember, we did this. Oops. The reason why this becomes that is from what we just defined. So if you went through and substituted this in for delta G here, eventually you would come to the Nernst equation. It's the same thing, just in a different form. Instead of in terms of free energy, it's just this equation in terms of the potentials. So I just thought I'd point that out because they look very similar. But right now we just need our friend Nernst. So let's kind of go through the same process. I'm going to have to find the correct half reactions and their potentials, the reduction potentials specifically. So let me go, I think it was nickel and lead, right? Let's look at, where's my table? There it is. So it's the nickel one again. So I'll just grab that because I know I need it. And then it was the lead 2 ion as well. So I'll just jam that in here somewhere for now. And lead. Da-da. Where are you, P? Oh, right here. That was easy. Very good, very good. Okay. Oops. Okay. And then we play with the fonts because, as I told you, it's my favorite thing to do. Someday all of these computer technologies will learn to play nicely together. And now we fix this because I have compulsive, whatever it's called, obsessive compulsive something. Okay, so let's kind of go through the same conversation. In this case, what's oxidized and what's reduced based on the numbers I just put there?
The lead ion is reduced, and then the nickel metal is oxidized.
Everybody cool with that based on the numbers? Okay. All right. So now in terms of the reactions themselves, once you recognize that, you know which order to put these half reactions in, because that's generally what they do is they give you a short table of reduction potentials, and you have to know when to flip things around to make it the right way. So like here, we have all the half reactions, but let's put them together. We know that the one with the higher reduction potential is going to stay the reduction. So that one stays in the order that it started. But we know that the one with the lower, meaning more negative reduction potential, is going to become the oxidation. So that one flips around. Now again, we picked some lucky winners here because everything's already balanced by the electrons already being the right number. That's not always the case, and we have to be careful of that. So we should do at least one example where that's not the case. It may not be in this lab because it's kind of hard to find ones that work well in the experiment, to be honest. So we pick the ones that we think measure the best, and that's why we pick these when we do the experiment. But again, here it's just a simple matter of showing the overall balanced equation. And remember, these equations are going to be spontaneous. Voltaic cells are designed to convert chemical energy into electrical energy. So they proceed spontaneously, and therefore we're always going to expect to get a positive E and a negative delta G. And of course, that means we're also expecting to get an equilibrium constant that's greater than 1. All of those are consistent with a spontaneous forward-moving process. All right, so that gets us the reactions part. So then who's our anode and who's our cathode?
The anode's the nickel and the cathode's the lead.
So anode is the oxidation.
Oh.
That's right. You said it right. Isn't that what you said?
Yeah, that is what I said, sorry.
So when you said, oh, you were correcting your correction, that you were correct? Or?
I was a little confused.
No, I was just confirming what you said because again, you can see the nickel is being oxidized. Oxidation happens at the anode, anox, and then where the reduction happens, the cathode. Okay. Oxidizing and reducing agent. Remember, this is that kind of flip-flop thing. Remember, if they're agents, they're going to be reactants, and they're doing the opposite of what the word says. So the oxidizing agent is the specific thing that was reduced. In this case, and I'm going to write it not in the diagram, it makes more sense to me to write it down here in the reaction. But the thing that was reduced has to be the oxidizing agent because in becoming reduced, it oxidized somebody else. The nickel, which you can see is being oxidized, must be the reducing agent. Is that good, or you get how that works because of the way the electrons are moving? Okay. Now for the voltage, this is a little different. We have to find the standard cell voltage first, but because these are non-standard concentrations, we're going to have to use Nernst after. So first let's find the standard cell potential, which is still going to be whatever the cathode reaction is minus the anode reaction, or again, you can think of it as the reduction one minus the oxidation one. It doesn't, I mean, it's the same thing. Or really what it boils down to, the more positive one minus the less positive one, right? If you think about it. So it's the negative 0.13, which is our reduction reaction potential, minus negative 0.23. And I think I can do this one without a calculator. Is it 0.36? I'm wrong. That's not 0.36. Isn't it 0.1? Is that right? Okay. I told you I couldn't do it. Just trying to make sure that we're all awake. All right. It's positive, but not by a huge amount because the potentials between nickel and lead are not that different. I mean, you can see that right from the thing. Okay, but that's not the actual answer because this would be only true if both of these concentrations were 1 molar. So now we have to think about it in terms of Nernst. So for the Nernst equation, the potential I'm looking for is the standard one I just found minus this correction of RT over NF ln Q. So now we just have to be careful that we know all the numbers in proper units, and we also have to understand what Q looks like. So here's the thing you have to be really careful of. The nickel here is a solid. The lead here is a solid, but these are aqueous. So we're going to use the same exact rules that we use in every context we do equilibrium or reaction quotients. It's products over reactants, and it's only the dissolved or gaseous species that matter. So in our case, and I'll start building this out now, we know that we're going to have E naught, whatever, RT over NF, and then the natural log of the concentration of the nickel ions over the concentration of the lead ions, and those are both raised to the first power because there's no coefficients in front of them. Could this look more complicated? Yes. Could there be more than just one over another? Yes. Could they have different super exponents? Yes. Just depends on the complexity of the redox reactions. But the basic format is the same. Now, before we actually calculate the values, let's take the numbers from what we were given and see if we can make some logical predictions. Because I think you can learn something really important, since most of the time Nernst on the AP exam is going to be conceptual. They're going to say, if we raise this concentration, what would happen to the cell potential, for example? So if you'll notice, the nickel is still 1 molar, so we're going to put that there. So this one is 1 molar, but the lead is being reduced to 0.01 molar. So let's just think about it for a minute. If you look at that numerical aspect here, just thinking of it like math conceptually, you can see that that ratio is going to be greater than 1. 1 over 0.01 is literally what, 100? And the natural log of 100 is going to be a positive number, isn't it? And that means this whole quantity is positive, so we're going to be subtracting a positive number from an already positive number. So that means our potential is going to go down. There's going to be a lesser driving force on this cell. Let's see if this makes sense conceptually looking at what's actually happening in the chemistry. Isn't the lead nitrate one of the reactants in the overall cell reaction? You see the lead nitrate is just, it's the lead ion, right? This in the net equation. And the other reactant is the solid nickel, but one of the products is nickel ion. So look at what we're doing here. Originally, if this were standard, this would have been 1 molar also, right? So what we're doing is we're creating a cell where there's less reactant concentration. Doesn't it make sense that if there's less reactant concentration, there's less forward drive? Like conceptually, right? Because if you do that, kind of extrapolate that to 0, once you run out of lead ions, you have no more reaction. The more lead ions you have, the more reaction you have. And in fact, it's not just more reaction, but more drive, more potential difference, a bigger, stronger force tending to push it through. So we should get a lower potential in this case. But we can make a generalization. And this is, again, what I think AP is largely going to test you on in this context. They're going to say, okay, if these are the concentrations, you don't have to do any math, but tell us how would this affect the potential? And you would say, in your mind, all right, is this a reactant or a product in the overall reaction? And if I'm making more, if I'm putting more product in, I'm actually driving it backwards. If I'm putting less product in, I'm actually driving it forwards. And if you get confused trying to remember that, if you just lay this out, you can reformulate the argument from scratch. As long as you understand how this sets up, it'll make sense as you change these numbers how mathematically it affects the outcome. Now, nobody's saying you can't plug the numbers in if you want to calculate it, but sometimes they may not even give you numbers. They may just ask you conceptually, and that's why I'm pointing that out. Let's actually put some numbers in and see what we get. So our starting potential was 0.1 volts. That's our standard. We have to subtract this RT. So the R, again, is the version that we're used to using. I'm going to leave it as 8.31 for now because that's in joules. And volts are in joules, if you recall. So let's make sure these units work out. That's the R. The T is at 298 Kelvin. Once again, our N, the moles of electrons that are being transferred in the process, is 2. So that's 2. And what's that? Our Faraday's constant is 96,485 coulombs, not coulombs, coulombs per mole of electrons, something like that. Okay? Well, these were moles as well. All right. So when you look at all the units, I don't know if we're needing to put the moles here because we need the moles to cancel out. So I think it's understood that these are in moles. So I don't think we need that unit there. But anyway, if you look at the units, these moles cancel these moles, these kelvins cancel these kelvins, and what is a joule per coulomb? It's a volt. And that's what we were looking for because, if we're going to subtract this term from this term, they have to have the same units. And then you're going to take the natural log of 1 over 0.01. And that's part of it. So that's what's going to modify this piece. And just like we said earlier today when we were looking at the RTL and Q problems, if you put the standard concentrations in, the natural log of that is 0, and it zeroes out the correction factor. And we're back to just the standard voltage. But here that's not the case, so let's calculate it. 8.31 by 298 over 2 over 96485, and then multiply that by the natural log of 100. So it's not a huge change, and I don't want that. I want you to realize that it wouldn't be a huge change. So you're like, well, that's not much. But what I get here is then 0.1 volts minus this whole piece is only about 0.059. And that means our final voltage, oops, is, I can't type 0.1 minus 0.059. That's 0.041. So there you go. Now, I don't remember if the little lab thing can measure this. Let's try it. How close it gives us. So let's see, we're changing zinc. What was it? What was our thing? It was nickel was oxidized, I think, wasn't it? So I just can't see both screens at once. And then our lead was reduced, but our lead nitrate's only 0.01 molar. And if we measure the cell voltage, uh-oh, something's wrong here. Are these the right ions? It says nickel 2 and lead 2. What is going on here, people? Is it my mistake or their mistake? I better go double check my calculator. Did you guys get the same thing I got? Nickel 2, lead 2, 0.01 on the lead. Let's just go back and double check and make sure I didn't type something wrong. I mean, I don't know how much I trust this simulation anyway, but it just seemed cool, so I grabbed it. I just, what? Oh, did you see a mistake?
No, what did the calculator just the simulation thing?
On their thing, it was like 0.068 or something.
Okay.
So that's why I just want to double check my numbers here.
I got the same thing as you, so I think it might be their mistake.
Okay. Oh, that's fine. I mean, no problemas. That's
Didn't it
weird.
do this to us last time too?
That may be right. You know, again, it's just they're just programming what we're doing in, and if they have different values for anything, that's going to throw it off. So I don't
Mm-hmm.
know. Yeah. Okay. I guess maybe this is not the best simulation to use for this. Okay. Anywho, you get the process. The cell note or the line notate, everything else basically follows the same. But let's just get this last piece together because I want to again show how the equilibrium constant comes in. We could theoretically derive an equilibrium constant equation by doing what we did for delta G. It should make sense that when the battery dies, when it gets to equilibrium, the cell potential would go to zero. And if the cell potential went to zero, Q would go to K, and we could write an equation that relates E to K. So you could theoretically use something like this to directly connect them. But do you really need to? Because if you find the Gibbs first, then you can always find K using the Gibbs form, meaning the exponential that we did here. So I don't know that you have to learn a whole new equation and mess around with it. It's really 6 of one, half a dozen of the other. But to get the Gibbs energy as we learned today, we just do one of these deals, right? So why don't you guys try that one and let's see what you get this time and then get K. And I just want to give you guys a chance to solve it. See if we agree. Oh, be careful because I know what you're going to ask. I have to be a little more careful here. Um, since we're doing this at non-standard, we're actually, these equations still apply, but what we're using is the new delta G, the Nernst, you know, like the corrected one. So just be careful of that. Let's see if we agree. Let me know if you get a delta G and I'll see if I agree. In kilojoules, please.
Yeah, or you would use the E you got from the like the adjusted one.
Yeah.
Okay.
Let's see. I got something up in here. Is that? Yeah, I'm agreeing with what I see in the chat. Like negative 7.9-ish in kilojoules, about. And then let's go ahead and keep going and let's find the equilibrium constant based on that. Watch your units. All right. I got something, but I think I screwed it up because I forgot to put in my. Oh, I put a negative. Sorry. Let me do that again. What'd you guys get? What'd you get? Yeah. And then let's ask ourselves if that makes sense because delta G is a pretty small number magnitude-wise, so K should not be that big of a number either. Delta G is negative, and delta G being, yeah, you're done, so that's good. And delta G being negative is another way of saying it's spontaneous, another way of saying it goes forward, and so is a K greater than 1. Also agrees with that. Also agrees with a positive voltage. But as we saw, the voltage being so small indicates there's not a very strong drive. There's not a lot of work left we can get out of this. All of these things connect. When you think of how all of these are telling the story, it's spontaneous, but it's not driven very strongly. We can't extract too much work out of this system. It's going to favor the products, so it's going to go forward as we expect. And again, there's not much of an electrical potential difference. All this is connected through the Nernst equation by saying we don't have much reactant to work with here, the way we set up this system. If we wanted to drive a much higher voltage, we would arrange it differently. In other words, we would probably, for example, if we switched this to 0.01 molar and this to 1 molar, we would have a bigger potential difference. Right? It would, in other words, it would invert these numbers, and we'd get a negative. We'd subtract the negative, add a positive. It wouldn't be much bigger, but it would add the 0.059 instead of subtract it. If we had flipped the numbers, is what I'm getting at. Is that good so far? So I was going to start electrolysis today. I don't know that we should. That's a whole other big topic, and I'll hold on to that, I think, till next time. Hopefully by then we'll have a different schedule of how we're meeting for these. We'll have more people able to attend, and that's another whole topic. So I don't want to dive into it. I think if we've understood this a little better today, that's a good place to stop. And we added that other piece, the NFE. If you want to try one or two more of these on your own, I think this one is good because you'll notice that this is a +3 ion and this is a +2. And the main thing I'm telling you this for is that when you balance this one, you're going to have to do multipliers like we did when we did redox. But what's most important is there's going to be 3 electrons on one line, 2 electrons on the other line, and they're both going to give you a common multiple of 6 electrons, right? So that's what you use for N. You use the balanced number of electrons, the total electrons moving, just so that you're aware of that one thing. I mean, that's the main reason why we did this problem, because it really highlights that point. But with that, I think we can call this one done. Do you have any questions?
I have a question.
Yeah.
For this one, would you also use the Nernst equation because it's not like standard 1 mole?
Yeah, absolutely. Which means you have to first solve it without Nernst to get the standard one, and then plug it into Nernst to fix it. Yeah.
Okay.
Absolutely
And then,
right.
is there a key for this?
Not yet. I might have one at home that's not online. I can probably just scan it in and put it up for you.
Okay, cool.
And that reminds me, since you said that too, remember there's more practice. I keep clicking on the wrong things. There's more practice in this arena. Going back to the that one document that had all the different problem sets on it. So we're still kind of in the third realm, where now we can actually solve the Gibbs part and the Nernst parts. So I'm not saying you have to do all this, but you should be able to do it. Like if you look through it, you should be able to solve those. And for this, did I already put a key up? I don't remember. Let me double check. No, 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 no. You know what? It would be on my webpage. Yeah, the problem set already has the key, so you can check those as you go. So I know it's awkward because when I'm actually looking at you to talk to you, my camera's over here. And so as I look to actually speak to your face, I'm looking away from your face. It's a very awkward setup. So now I'm talking to you, but I'm looking at my computer, so I can't see your reaction. Now I'm doing this. Anyway, any other questions? Okay, we're really close, honestly. If you've been to the kinetics lessons, and that's not to say you're an expert, and you've been to these lessons, we're literally like 1 or 2 lessons away from completing the entire curriculum. and then we're just in review mode. So we're almost there, folks. All right.
Thank you.
Thank you.
Thank you.
Have a
Bye. Have a nice
lovely weekend.
weekend.
You too. Thank you.
I just have like an overall question because like I've never taken the AP test on like line,
Uh huh.
but like with